Hello friends, welcome back to my channel. In this video, I am going to solve exercise question from book Topics in Algebra from chapter 4 Vector Spaces and Modules. Question is, if V is finite dimensional and T is a homomorphism of vector space V onto V, prove that T must be 1, that is T is injective, and so T is an isomorphism. So proof. Let V over field F is a finite dimensional vector space with dimension of V is equal to n. And set B consisting of n number of vectors, say E1, E2 up to so on En, is a basis of vector space V. That is, B spans V and these n number of vectors are linearly independent. Further, we know that T from vector space V to V is an onto homomorphism. Now since T is onto, we have image of T will be equal to vector space V. Now our claim is to show that T is 1, that is T is injective. Now to show T is 1, it is sufficient to show that kernel of T is singleton 0 vector. Further, let us consider T of E1 is U1, T of E2 is U2 up to so on, T of En is Un. That is, the n number of vectors U1, U2 up to so on Un are images of the basis vectors E1, E2 up to so on En under T respectively. Now we will show that these vectors U1, U2 up to so on Un is a basis of vector space V. Note that for any arbitrary vector V in vector space V, V can be written as the linear combination of basis vectors E1, E2 up to so on En in this unique way, where AIs are all scalars coming from field F and these scalars are unique. Then we have T of V is equal to T of this linear combination, that is T of V is equal to T of A1 E1 plus A2 E2 plus and so on plus AN En. Again, using the property of homomorphism, we can write T of V is equal to A1 T of E1 plus A2 T of E2 plus and so on plus AN T of En. Again, this can be written as, since images of T of E1, E2 up to so on En are U1, U2 up to so on Un respectively, so we can write T of V is equal to A1 U1 plus A2 U2 plus and so on plus AN Un. Now from here, we can observe that the vector T of V belongs to span of these n number of vectors U1, U2 up to so on Un. Now since T of V is any arbitrary vector of vector space V, we have span of the n number of vectors U1, U2 up to so on Un is equal to image of T. Now since T is onto, we can write span of U1, U2 up to so on Un is whole vector space V. Further, we have one corollary which states that if V is finite dimensional vector space and U1, U2 up to so on Um spans the vector space V, then some subset of these m number of vectors V1, V2 up to so on Vm will form a basis of vector space V. Now note that here these n number of vectors span vector space V, and at first we have considered that dimension of vector space V is n. Therefore, these n number of vectors will form a basis of V. And so we have, by above corollary, the set say B1 consisting of n number of vectors U1, U2 up to so on Un is a basis of vector space V. That is, B1 spans V and these n number of vectors are linearly independent. Now let us consider any vector, say U in kernel T, such that U has representation of this type, that is U is equal to alpha 1 E1 plus alpha 2 E2 plus and so on plus alpha n En, where these alpha i's are unique scalars coming from field F. Now since U is any arbitrary vector in kernel T, we have T of U is equal to 0 vector. We can write this as T of alpha 1 E1 plus alpha 2 E2 plus and so on plus alpha n En is equal to 0 vector. Again, using property of homomorphism, we can write this as alpha 1 t of e1 plus alpha 2 t of e2 plus and so on plus alpha n t of en is equal to 0 vector. Now we know that t of e1 is u1, t of e2 is u2 and t of en is un. So we can write this as alpha 1 u1 plus alpha 2 u2 plus and so on plus alpha n un is equal to 0 vector. Now we have shown that these n number of vectors u1, u2 up to so on un forms a basis of vector space V. So these are linearly independent. Now since this linear combination is equal to 0 vector, so using property of linearly independent vectors, we must have these n scalars alpha 1, alpha 2 up to so on alpha n are all equal to 0. Therefore, this representation of u becomes u is equal to 0 e1 plus 0 e2 plus and so on plus 0 en, and so u will be equal to 0 vector. Now since u was any arbitrary vector in kernel T, we have kernel T is equal to 0 vector, singleton 0 vector, and so T must be injective, that is T is 1 1, and therefore T is an isomorphism, and this proves our result.